Okay. So, um, you look at like Feynman diagrams and stuff like that, and we have like these interactions that use virtual particles. And basically, we can't observe these particles, and these interactions happen so fast that like we don't really actually see these interactions happening, but we know that there must be some sort of interaction happening to cause repulsion. And so we created virtual particles to explain this interaction, explain the effect we see, even though we don't really know the cause. And we say that virtual particles, we treat them like real, right? Because we know something's happening there and we use them to help define this interaction, but we don't actually think they're real in the sense that they're there, because basically these particles are coming into existence and then going out of existence really quickly. That's also another thing. But I don't. These virtual particles aren't virtual. They're just, as I just said, they're too small and too fast for us to really observe. But I do think that, as I've said it before, that all the particles are radiating energy, and this radiation of energy is these virtual particles that are causing these interactions to happen. They aren't virtual particles; they're real. We just can't see it because this energy radiation on the scale of an electron or a proton is completely different to the energy radiation of a collection of like a block of these atoms put together. Like, because when you think about how many atoms are in like a little cube, there's I'm pretty sure billions, maybe I don't know, there's a lot, right? I don't know the exact number, but I imagine it's at least billions. And when you add up all of that radiation energy together, you notice that there's some radiation, not necessarily radioactive radiation, but like, or like ionizing radiation, I think is the right term there. But just infrared radiation, or maybe even colder, right? But there's radiation coming off of the cube, even though it's just like a solid cube. And that's just the combined like radiating of these particles at the subatomic level, at the quantum level. They are radiating these virtual particles that aren't virtual, and that amounts to something greater. Um, and that's kind of what's running everything, is them sending out these this radiation of particles. And I feel like photons are just stronger, or like are just higher energy versions of these particles, right? So we notice photons because they have high energy. And I think that this high energy of photons is something that we can notice because of how much energy they have, right? Um, but the majority of this radiation is not at this high energy level, because you know they're trying to take in and send out energy. Basically, they're not trying to dump it as fast as possible. They're trying to do something with it. So it's kind of like a slow leak, unless they have to, like, unless they got too much and they've got to dump it to get back to like a balanced state. um, but I don't think virtual particles are virtual. And I think, I don't know if this is what vacuum energy is, but the like vacuum energy particles, where they basically come into existence and then they um, like annihilate it themselves on on a really fast time scale. So it's basically like they didn't exist. They existed, but they also basically didn't exist at all. And we call these also kind of like virtual particles, because it's like this fluctuation in like a vacuum. So we have like this energy fluctuation in the vacuum, and we call these basically virtual particles too. But I don't think that is virtual particles. And I think that observing this effect is basically a hint of how our universe works, because we're watching these particles basically pop into existence and then annihilate themselves on a time scale that's like either not observable or barely observable. And we say, oh well, they basically didn't exist at all. But it may be crazy to say this, but our entire universe could be one of these single blips of a virtual particle, right? Because all it is existence coming into existence, but with a counterbalance, right? And so it's saying we exist, but we also don't, because we still equal zero. But obviously we're existing right now. And and it may be weird to think this because, when these particles come into existence, it's like, so there's basically no time at all happens before they're gone. But they're also like, our concept of time is relative. So who's to say that our entire universe's existence and death will be encapsulated in a single instant of another's? There's really no reason to say that can't be the case. Because to us, it doesn't matter how fast time is moving to an outside universe. It's irrelevant, because that universe is so much greater on the grand scale than ours that it's basically empty space to us, right? There's not actually anything there, because there's so much, like, atoms have a lot of empty space, right? So imagine that you're in a universe where the universe itself is basically an atom, right? Then imagine how much empty space you would be sitting in, right? It would feel like there's nothing around you, that you're in a void, but you just can't see far enough to see anything else. And when you're on a scale so tiny, time moves really slow to you. Because you're so affected by the gravity of the particle that you're inside, right? Like, if you're inside the void of an atom, basically, time would move really slow to you, because you're on your scale, there's a great amount of gravity, right? But that's your constant level of gravity, so you don't even notice it. But what if we think time is moving really slow because we're so tiny, and it's actually an instant? Because I've talked about this before, but I feel like there is some math. I feel like we have some discoveries and some mathematics that back this up, that our universe is, and that's all our universe is. And that's crazy, right? That we are watching this happen. This vacuum energy is happening all around us, right? All the time. And every single time we observe that's an entire universe coming into existence and disappearing. That's crazy, right? And if it's not that, then at the very least, it is a remnant of how our universe began in the first place. Because when we watch this, fluctuation of things coming into existence and not, all you need is one instance where enough come into existence in the same spot at the same time to create enough energy to create something. And I'm going to talk about how there's something in the universe compared to nothing in a minute. Not in this video. But basically, I think antimatter didn't fully annihilate matter for a reason, and I'll talk about it in the other one. And so we observe something being here because enough energy was sent out for it to happen. But if there's not enough energy there, then it just collapses again. And so every time we see these, you know, virtual vacuum particles, what we're seeing is potential chances for energy to, you know, be created. And I think that if you had enough vacuum energy combined in a certain spot, it would be like a chain reaction sort of thing, kind of like fission, where, you know, it sends out basically, I think, electrons or whatever, and it smashes into other atoms, and those atoms get broken apart, and it causes this chain reaction of atoms smashing and releases, leads to, you know, new bonds forming of these atoms, getting them back to balanced energy states, because once you split that atom up, it can't just put itself back together. It's lost. It doesn't have the energy to sustain that, so it needs to find a new balanced energy state. And so, depending on how much of its nucleus it lost, it has to then, you know, combine itself and find a new balanced state, but then it has a ton of excess energy that it was using to help hold them in place that it no longer needs, right? And that's where this release of energy is coming from, is from this excess when you reduce the energy state of the nucleus without reducing the energy state of, without reducing the amount of energy that it has. And basically, when you get this combination of vacuum energy, you create photons, and these photons go out and they create enough energy to cause other vacuum virtual particles to have enough energy, and you get this basically, you know, explosion of energy. And all of this energy, once it's in that excited state, lingers. And that is how we because I'll touch on it slightly here. When these virtual particles get hit with this energy, right? You have these two particles that are perfect opposites. But all of a sudden, one gets hit with energy. Well, now this one is a higher energy than this one is. And when this one tries to annihilate, some of this one's still left over. And so it's now no longer virtual, as we call it. It's real. This is a real particle now. And so I think that these virtual particles that we're seeing are basically how our universe came to be. And if they're not their own universes in their own selves, which they could be, I think, then at the very least, they are the remnants of what happened. And I think that energy, those particles, are either on the photon level or smaller. And photons, as we see them, are actually more of a combination of photons. Like, we call it like an energy packet, but I think like a photon is probably a photon packet. A gluon is probably a photon packet. Quarks are potentially just photon packets, right? It's just larger and larger amounts of photons to create a like a mass of energy, and they just kind of fly around. Like I don't know. I don't know if it really makes sense to try and think of the fundamental particle. Like, the atom was supposed to be the fundamental particle that couldn't be split, and then we found out that we can split it. So I don't know if it makes sense for me to say that a photon's probably the fundamental particle, because you know, um, I'm not sure there's really a limit to how far down we can go. um, it's just a matter of there's a limit to how far down we can go, but I don't think it's defined by. But that's defined by us and our limitations, not by how far there is. Right? There's a distance we can see out into space, and that's not defined by the distance that there is of space. It's just how far we are able to see so far. Right? It's a limitation on us. It's not a limitation of what's actually there. And so I think photons might be the bottom of what we can observe, but I feel like that statement is also very easily falsifiable in the long term. So we'll have to see. But I think that a lot of the subatomic particles we're seeing are mainly just photons in different quantities. And when something has more energy, it has more photons, which would also make it have more mass. And as we've said, I mean, we could kind of think of it. I mean, this is kind of going deeper than I thought right now, but we said that particles, right, matter, mass, is made up of these particles. These particles are radiating energy, right? And so when they're radiating this energy, they're continuing this cascade effect, right? But at a scale that's smaller now, because there's not as much just vacuum energy around as there was initially, right? So we have, as I've said, there's basically we're made up of basically empty space for the most part. So when in this void of energy, these particles are sending out radiation, and this radiation just may not be crazy strong, right? But when it interacts with these virtual particles we see popping in and out of existence, if one pops into existence and gets hit by one of these photons, tiny virtual photons, all of a sudden it imbalances that equation, and you've got a new photon, right? And so what if energy comes from these creation of photons, right? These photons are created by sending out radiation. It creates new photons. These photons are brought into a system to continue its mass, right? And then over time, these photons do eventually lose their energy and then finally go back out of existence. But by that time, they'll have created more of its own, more energy itself as well, and created more new photons by emitting these smaller photons. And these photons just kind of collect together, because when they're together, they can emit a higher concentration of photons and maximize the amount of interactions with vacuum particles, basically, and create more of these photons. This is high speculation here, but photons are basically the tiniest unit of mass we can get, right? We think that light moves at the speed of causality, or the fastest we can possibly go in this universe. And maybe that's because they are the tiniest unit of mass. But this mass is just the condensing of dark energy, right? This vacuum energy. The energy that is creating these virtual particles that come into existence and collapse on themselves and annihilate. We are seeing this happen, right? And every once in a while, not really every once in a while, it's constantly happening, but doesn't necessarily happen with every particle that comes into existence. But we see them pop in, right? And then they get hit by a photon, they don't cancel out, and then this mass is now energy. Like, we're getting these, like, this, like, almost like the flow of time, like the flow of this dark energy is flowing by, and on the outside of the pipe, like, condensation is forming, right? And then this condensation is the energy that we can use, right? And so underneath, say we have like a drip pan underneath, we get this condensation on the pan just dripping down into the condensate pan, and then that's the energy that we're able to use, but it is just the tiniest fraction of what's actually like the energy that's flowing through the pipe, right? But to us, we've got like tons of energy. And so it's dripping in and it's collecting in this condensate pan, and maybe the condensate is then flowing back, is then creating a flow, like it's in a pipe of its own, or it leads into a pipe of its own, and then you've got a flow there, and then that flow is maybe that that water still has heat, right? So then you've got your condensate pipe releasing heat, and then that energy can be used by something, right? So we've got this trickle down effect of energy, and so we think we are using this great amount of energy, and we're just using the heat that's coming off the water that's being created from the dripping, the condensate on the pipe or something, right? Like, we think, I don't know if that makes sense. We think we're using like this crazy energy source, right? And we're just using the excess radiation. Like, we're not even close to what true energy is. Yeah. So that went a little farther than I thought, but the thought came to me. So anyway, peace out.